Greetings, welcome to the video on section 4.1. So we're going to talk about or review some concepts from earlier in the course and extend those into the future. This starts probably one of the most important chapters of the textbook, and I really want to encourage you to make sure you do an active read in this chapter and that you've got your comp book out and you're taking notes and really paying attention to the concepts. So before we get going headlong into this chapter, I thought it'd be a good idea to do a little bit of review, and then we'll come back in a second video in chapter 4 where we'll actually work some problems from this section, okay? So the title is variability, in estimates. That's what our title for this particular section is. But before we get into that, as I just said, I put myself a slide here to remind myself, is to make sure you read this carefully and keep good notes in your reference book. And we're going to go ahead and review some concepts and reiterate some of the findings from the earlier part of the course, okay? All right, so before we get into talking about the new stuff, a quick review of the idea of shape and when it applies and when it doesn't apply. So take a second and write down what you think the shape of this distribution is. I'll give you 5 seconds. Okay, great. As it turns out, it doesn't have a shape. It's not applicable. Why is it not applicable? I'm going to spell applicable correctly here. Why is it not applicable? The reason it's not applicable is because if you come down and look at the data axis here, the x-axis here, this is categorical. And categorical variables, unless they're ordinal and have a natural ordering to them, there's no way you can order them across the x-axis. I could have come back through and done this alphabetically and would have got a totally different shaped distribution. So when we're talking about shape, when we're talking about the shape of the distribution, we're talking about numeric data. So we need to get rid of the categories and put things into numbers if we want to start talking about shape. All right, so keep that in mind. That's a little bit of review of a concept that some folks find a little sticky. Let's try another sample for another example that will hopefully drive home the concept of sampling. So I'm going to give you 30 seconds here, and what I want you to do for me is I want you to go through and look and count the number of F's that you see in the following sentence. Okay, you should be about finished by now. That's should be the number of F's you found. So how many F's did you see in there? Did you see 5? How many you saw 4? How many you saw 6? Well, let's go see if we can actually count them and see if we can find it. So let's see, there's 1, 2, excuse me, 3, 4, 5, 6. Let's see, did I get them all in there? Let's try one more time. So 1, 2, 3, 4, 5, 6. So it looks to me like there are 6 in there. So did you get 6? Many people get less than 6. Well, why did they get less than 6? Well, because the F's in the word of, right? You just skip right over those. You don't even see them. So notice you were supposed to take a complete census of the sentence. You were supposed to come in here and find exactly how many F's there were in the sentence. Yet, even with a complete sentence or a complete census, in other words, where you go in and you get all of them, it's not unusual to make a mistake and miss some of the values. As it turns out, getting a census is incredibly difficult many times, and so we typically will sample when we go to do any sort of actual data analysis. There is this thing we do in our country every 10 years, is supposedly we do a census, but as many people will tell you, it probably would be better off if we did a sample. We'd probably get a much better estimate of the number of people in every state if we did it that way. But that's for a different topic. Okay, quick review of some words. What do we mean here by population? What do we mean by unit or subjects? What do we mean by sample? What do we mean by variable? Size of population, size of sample. So let's go back through each one of these rather quickly. So the population is the entire group of objects. And if, as in the last sentence, the population was all the letters in that sentence, and if we wanted to calculate all of the F's in there, we would have taken a census from that population. And a census means that we go in and we gather up exactly the amount of items that fit the particular variable that we're looking for. Okay, in the case of what we were just looking for, the variable we were interested in was the letter F. So the size of the population is n. That would be the total number of letters in that sentence. The size of a sample would be, say, if I went in and just took a random sample of, say, 10 letters out of that entire sentence. Okay, that would be a smaller size than the entire population. If the sample is equal to cap n, then we have taken a census. So let me give you a little drawing here that may help make this make sense. Whoops, sorry, went past there. It's the famous egg with pepper on it drawing. So let's say in this particular example right here, cap n is equal to 16. In other words, there are 16 pepper flakes on our egg. And we go in and we take a simple random sample of size n4. It just happens to be the yolk that we took it from. It's just, that's the loop, is to indicate that that's the sample. So notice that each of the units are these pepper flakes, or these black dots here. The population is the loop. That's all 16 of them. My random sample I selected from there is 4. Okay, so if I was able to go in back to the sentence for a moment and calculate say the percentage of F's, or the number of F's in that particular sentence, and I did it so that I did it from a census, then I would have gotten it from the entire population of letters, and I would have gotten the parameter. On the other hand, if I'd taken a simple random sample of, say, 10 letters from that sentence, then that would have been a statistic. And a key thing here is that statistics come from samples. So S goes with S. And population values are referred to as parameters. So if I wanted to calculate the percentages of F's in that sentence, and I did it by counting all the number of letters in there and dividing that into the number of F's that I saw, that would have been the parameter for the percentage of F's. Okay. A statistic would have come from if I'd, say, taken a simple random sample of size 10 of all the letters, counted the number of F's that were in there, and divided that through by 10. Okay, so one of the key jobs, one of the key things in statistics is to realize that what we're trying to do is estimate the parameter with the statistic. There was many times, I was saying, we're not able to actually get to the parameter. So instead, what we do is we take a sample, and that sample statistic is our best guess of the population parameter. So statistics' job in life is basically to be a parameter estimator, or to make an estimate of what the parameter is. So a statistic is an estimate. That's a good way of defining it. It's an estimate of a population parameter. I mean, you could have called this course, instead of statistics, you could have called it parameter estimation, and that would have been, more descriptive, but not possibly, that useful. Okay, so let's see if we can take an example here and see if we understood everything that I just said. So 9% of U.S. households, or the U.S. population, has type B blood. In a sample of 400 individuals in the United States, population 12.5% were found to have type B blood. So circle the answer in the following. So in this particular situation, the value of 9%, is that a parameter or is that a statistic? Well, the key thing is that the 9%, where did that come from? That came from the population, so therefore it was a parameter value. And then ask us, where did the 12.5% came from? Well, that came from a sample, and since that was a sample, then the 12.5 value is a statistic. That's a really important concept. Make sure that makes sense to you, so you know the difference between a population parameter and a statistic. All right, let's go on to slide 10 here. Wendell Zerkowitz, slave to the waffle light. So Wendell there has got himself a fancy waffle maker, and he makes waffles, and there's a couple things that Wendell is going to want to know about his fancy waffle maker. He's going to want to know, first of all, what is the average time for it to cook? In other words, how long does it take for each waffle to cook? And then he's also going to want to know something about the variability in the cooking time. So Wendell can go in and cook a bunch of waffles. And if he cooks a bunch of waffles, whoops, excuse me there, what he's going to get is he's going to get an estimate of the average amount of time it takes for a waffle to cook. So if he takes a sample, right, of the cooking times, what he's going to get is a sample average. And if he takes a sample and he wants to know something about its variability, in other words, this is going to tell him something about the average amount of cooking time, right? And then he's also going to get from his sample something about a measurement of the variability, and so he'll get what's referred to as the sample SD. Okay, now the sample SD and the sample average both get their own notations. The sample average is given by X with a bar over the top of it. The sample standard deviation, that's given by S. Now, if you recall from previous work, when we were talking about working with a normal distribution, we know that the parameters for the mean and the standard deviation, the parameter for the mean, we know that that was given by mu, and for the ST, for the standard deviation, we know that that was given by sigma. So X bar is going to be what? Well, it's looking to approximate mu, and S, its job is to approximate what sigma is. So, let's see here. Go back to my tool to find the right slide. The sample means notation, again, was given by X bar, and the way we calculate that, the calculating formula was if Wendell cooked 25 waffles, right? He would take those times, those would represent X, he would take those 25 times, he would add them all together, and then divide by 25, and that would give him his sample mean for his average amount of cooking time. Well, contrast that to, excuse me here, this thing's taking a whole time to switch. There we go. The population mean, which is given by mu. Now, what's the difference in the calculating formula between the sample mean and the population mean? Well, it's relatively small change, is we changed from little n to cap n. And if you recall from the previous discussion, cap n is what? Well, that is the population size, okay? All right, so similarly for standard deviations, we know that there's going to have to be a sample standard deviation formula and a corresponding population standard deviation formula. Now, don't sweat this formula too much because it's obviously in our studio. We've been working with it quite a bit. We know that SD gives us this. But just a quick explanation of what this is. It says sum the distance between the X and the X bars, square that distance, add them all up, divide by the number of samples minus 1, which we'll discuss in a future video that this is called the degrees of freedom. And then since we squared things, take the square root of it, and what you get back is what we had been talking about all along. You get back the average distance away from the mean. In other words, it's not exactly what it is, but that's for if you're going to talk to people in general, that is pretty much what the standard deviation does. It measures the average distance all of your data points fall away from the mean. And so the larger that value is going to be, the more spread out your data is going to be, and the smaller that value is, the more clumped together your data is going to be. Okay, well, if there is a sample version, of course, then there is a population version. The difference is you divide by cap n instead of by little n. That's little n minus 1. That is, so there is a difference in the calculating formula, and you'll actually get different values for sigma versus S. It's not a huge consequence for us because almost always, pretty much 100% of the time, we're working with samples, so we're going to be dividing by n minus 1. Okay, so this is comp book worthy. this is something you should definitely have in your comp book, and that you need to also have top of the head. These, I know I said it, we're going to make you memorize too many things, but this is something you need to memorize. So flashcards, post-it notes on your bathroom mirror, whatever it takes, okay? You need to know that mu, its estimator, is x bar. And you need to know that sigma's estimator is s. In other words, that's the statistics. And p, the population proportion we saw back in the binomial, its estimator is going to be given by p hat. Okay, so you need to know who are the estimators for our particular population parameters that we're working with. That notation is going to be real important as we move along, all right? Okay, now let's switch in to start talking about the new stuff, in particular the stuff from section 4.1. If we take a single sample, then from a population, and we use this sample to estimate the parameter, then this estimate statistic is called a point estimate of the parameter. So if Wendell cooked 25 waffles and estimated the cooking time of those 25 waffles, he would have made what is referred to as a point estimate of the parameter. He would have had a single estimate of what the actual population parameter is for the cooking time for his waffle maker. So that is a statistic. A point estimate is a statistic because it comes from a sample, and its job again is to estimate what the parameter value is. So if I give you a single value, then I have given you a point estimate. That's a key thing. Now, if I go through and I take a look at where that particular estimate came from, the thing we need to realize is that if Wendell cooks another 25 waffles, it would be highly unlikely that he's going to get the same average cooking time as that he did with the first 25 waffles. And if he cooks yet again another 25 waffles, he's going to get yet a different average or a different sample mean. And so the thing to realize is that there is variability in our estimates, is that our estimates change from one sample to the next. They're not going to be the exact same every time. That's almost intuitive. Most of us would assume that to be true. That if I send everybody out in the class to go buy a waffle iron and say, okay, go cook 25 waffles and give me the average time and then give that back to me, and we collected up all 34 of those data points and we plotted them, we would see that they would not all fall right exactly on top of each other, that there would be some variation in them. Okay, so that distribution of sample means that you all would turn into me of your cooking times for your waffles, that's called a sampling distribution. And the sampling distribution represents the distribution of the point estimate based on samples of a fixed size from a certain population. It is useful to think of a particular point estimate as being drawn from such a distribution. Understanding the concept of sampling distribution is central to understanding statistical inference. And that's one of the key things we are doing in this class, is statistical inference. So you want to make sure you understand what that box right here said. This is a very important concept of what do we mean by a sampling distribution. Now, the standard error of an estimate, the standard deviation associated with an estimate, is called the standard error. It describes statistical error or uncertainty associated with the estimate. A good way of thinking about the standard error of the estimate is, again, it is a standard deviation. It is a standard deviation of our sampling distribution. So the standard deviation of the sampling distribution is the standard error of an estimate. How do we compute that? As we'll see, it's very useful to be able to calculate that number, and as it turns out, we can show mathematically that given n independent observations from the population with standard deviation sigma, the standard error of the sample mean is equal to sigma divided by the square root of n. A reliable method to ensure sample observations is independent is to conduct a simple random sample consisting of less than 10% of the population. After that, things get a little bit sketch. But if we get a good size sample from a population and it's less than 10% of the population, then we're good to go. All right, so one of the sampling distributions we're going to be really interested in is the sampling distribution of the sample mean. And so this is the standard error for the sampling distribution of the sample mean. There is a lot going on this slide. Make sure you copy this stuff down into your reference book and leave some space in there to come in and fill in more information as we move through this material. Alrighty then. So one more time, so we make sure that we have a little bit of a reminder of who our two most favorite parameter estimators are at this junction in the class. X bar represents the sample mean, mu represents the population mean, p hat represents the sample proportion, p represents the population proportion. So knowing which of these two parameters that we're working with, or which of these two that we're trying to estimate, is a huge first step in understanding how to do confidence intervals and hypothesis testing. So we're going to start off the exercises for this section by looking at some examples where we decide what is a parameter and what would be an estimate. And again, one more time, the two most common ones we're going to be working with are going to be the mean and the proportion. All right, so I'll show you what's next here, and then we're going to go ahead and take a pause and come back. Okay, so we're going to take a look at 4.1, where 4.1 is identifying the parameter part 1. And so we'll take a pause here, let you digest what we just talked about, and we'll come back in a minute and we'll actually work this problem.